All right. Thanks for coming. So we're continuing our discussion on schemes, and we're going to study two particularly nice properties of schemes today, which is normality and factoriality. So this is the paragraph 5.4 in Vakil's notes, so normality and factoriality. So let me tell you this. So as a motivation, Vakil, for studying them, Vakil mentions the following. He says, okay, locally, we will see that locally Noetherian normal schemes satisfy Hartog's lemma. Now raise your hand if you didn't understand anything that is actually mean. Thank you. That's myself as well. So I don't know, but this is basically the motivation. I guess satisfying Hartog's lemma is a good thing. But we're going to see it only in chapter 11. But we're right now in chapter 5. Anyways, so normal schemes are nice. That's the feeling that we should get. So let me begin with definition. There'll be a lot of ring theory, and actually many ring theoretical facts. I'm just going to say, oh, it's basic ring theory. You prove it on your own. Pretending that I actually know how to do it. So the definition, we're going to start with the following definition. So A is an integral domain. And we say that A is integrally closed. Now pay attention. If for any polynomial f of x, for any polynomial f of x, which is taken from the ring of polynomials with coefficients in A, which is monic, and such that its root alpha satisfies alpha lying in the fraction field of A, then in fact alpha must be in A. Super confusing, right? What the hell is that? Actually, it's not that bad, and I'm going to give you some examples. Let me explain it in a simpler way.
So
this is a
every
ring.
root that is in the fraction field satisfies this fraction.
So let me show. I think that there's a much more intuitive way of describing it. I take A, okay? I'm taking its fraction field, okay? And then I am computing its ring of integers of the fraction field. And what I want it to have is to be A. That's all that I want. That A is the ring of integers of its fraction field. So if you have this, that's bad. Does that make sense? Let's see an example of this fact. What's the most simple example of the integrally closed thing? Huh? The integers, right? So take Z, right? So compute its fraction field. The fraction field of Z is just Q, right? And then I ask, okay, what are the ring of integers of this thing? It's Z precisely, right? So OQ is that. So this is basically this classification, the second classification. Now let's take a look. This guy, what is this thing actually telling us? I'm going to give you my favorite example. Consider, so this is the second example, consider Z adjoint root -3, right? Ring, like very nice. And what I'm going to do is I'm going to, it's easy to observe that Q adjoint root -3 is its fraction field. Do you guys see why? Right? So, but then here's what I'm going to do. I'm going to take a polynomial f of x. This is a polynomial like this, okay? And as you can see, this polynomial, so this, I'm going to call it A. And this polynomial is in fact in AX. Do you agree? Right? And if we're going to take a look at one of its roots, then say at this one, and this is just the third root of unity, then third primitive root of unity, then you see that it actually does lie in the fraction field. So it's actually in q root negative 3, right? But it is not in z root negative 3. In fact, so you can see that z root negative 3, adjoint root negative 3, is not integrally closed. In fact, and this is not too difficult to prove, if you would adjoin alpha instead, the third root of unity, then this guy would be integrally closed. Okay? So are we good with these examples? So then let's move to the definition of a normal scheme. We say that a scheme X is normal if all of its stalks, right, are integrally closed. Right? So, in other words, here's my structure sheaf, localize at P, right? Some prime ideal inside some element inside X, right? And I expect this guy to be integrally closed. And if this is true for all of them, then I have normality condition. All right. So this is a stalk. What is stalk local property, right? Now, let's move to some, so what do I want to mention? So let's start with, so let me mention the following proposition, that let A be integrally closed, and let S be a multiplicative subset of S of A without 0. Okay? Then this integral closedness property behaves well with respect to localization. So what I want to show is that, in fact, this ring, where I'm allowing elements of S to be invertible, then this ring is, in fact, integrally closed. So consequence of this proposition, right? Because, I mean, so if A is integrally closed, then all of its localization is integrally closed. So now we know that if A is integrally closed, then spec A is normal. Okay? This is just a consequence of this thing. Because, I mean, what are these stalks, right? These are just localizations, and we know that it behaves nicely with respect to localizations of A, and we know that it behaves nicely with respect to localization, right? Proof of this fact is rather simple. So let's, I'm going to use the definition right there. So let's see. So what do we need to show? So what I'm going to do is I'm going to pick a polynomial, f of x, right? I'm going to take this polynomial from S inverse A adjoint X. And we're going to say, so it's monic. And we're going to say that alpha is the root of f of x in where? In the fraction field of S inverse A, which actually coincides with fraction field of A. Agreed? So now, let me actually write down what this polynomial is. So say it's of the form x to the d plus c d minus 1 x to the d minus 1 and so on, plus c1x plus c0. Right. So now what we're gonna do is we're gonna note the following. Note that these coefficients ci all lie is in S inverse A, Well, what does that mean? It means that Ci is a very particular form. It's of the form Ai over Si, where Ai is in A and Si is in S. Agreed with that? Now so now what I'm going to do is I'm going to define this new number, which I'm going to call S hat. And this number will be just a product of S0, S1, up to Sd. Agreed? And now let's take a look at this equation, right? So plus Cd minus 1 x to the d minus 1 plus alpha d minus 1 and so on. C1 alpha plus C0 equals to 0, right? So alpha is the root of this polynomial. And what I'm going to do is I'm going to multiply by S hat to the power of d everywhere, right? So what we're going to get is, we're going to get S hat right here. Then I'm going to get S hat in front of here, S hat alpha here. And over here I'm going to get S hat to the power of d minus 2, C1 S hat alpha, plus S hat to the d, d minus 1, C0, S, no, like that. There we go, okay. Right, does that make sense? Oh, over here it should be d minus 1, like that. Okay, does that make sense? And now if you note what just happened in here, these coefficients now are all in A. So this is in A, this guy is in A, and this one as well. Okay? So in fact, on the left, we have a monic polynomial in A, right? And we have its root, S hat alpha, right? So, so this root, and because A is integrally closed, right? Now we know that S hat alpha must be an element of A, correct? But then it means that because S hat was in S, it means that alpha is in S inverse A. This completes the proof. Okay? So again, if our ring A is integrally closed, then spec A is a normal scheme. Okay? So that's very nice to know. Now I'm going to give you an interesting example of a scheme that is normal, but the original ring where it came from is not even an integral domain. So, and I'm very thankful to Nick for helping me out to figure out this example. So let me write this down. So example. So the scheme spec K, disjoint union spec K, which coincidentally is also isomorphic to spec K cross K, and which also coincidentally isomorphic to spec Kx mod x times x minus 1, is normal. But it is not integral. Does that make sense? Now, so this fact, by the way, was proved in lecture 13 by Nick. So, not this one, but I'm fairly certain that it's true. Anyways, K is a field, by the way. So let me mention this. So K is a field. Right. So how would you see that it is not integral? That's kind of simple. I mean, if you would look, I don't know, for example, somewhere over here, right? Just look at, I don't know, look at its functions, right? On this topological space, right? You have a function x, right? You have a function x minus 1. Neither of those are 0, but their product is 0, right? So, right? So it's not an integral scheme. However, it is normal. And in order to see why it is normal, we need to understand that guy, okay? So let me define this ring, Kx over x times x minus 1. And I want to understand what is spec A. So if you don't mind, I'm going to actually call this ideal M, just for brevity. So what is spec A? Well, Kx is a Euclidean domain, right? So it's a PID, so it's a U of D, very nice. And so what we're going to do is we will understand that there is a correspondence between the prime ideals of this ring, A, and the prime ideals of this ring that contain M. So in other words, this spec A consists of all prime ideals that contain x times x minus 1. So this correspondence was actually pointed out to me by, once again, I did probably every professional ring theorist knows these facts, or algebraic geometry or something. I don't remember it. I know that it's kind of obvious and things like that, but I don't remember it, and Hassan reminded me, and you reminded me of this, so yes. But so we have this prime ideal containing x times x minus 1. Now this prime ideal is in Kx, and Kx is a PID, which means that there is just one single generator, which I'm going to call F. But now such a containment is only possible if if this generator F in fact divides x times x minus 1, right? And from here we can see that this means that F is either x or x minus 1. So in other words, what we managed to show is that in fact spec A consists of two things. First, it consists of x mod m, and it consists of x minus 1 mod m. So there's two prime ideals inside spec A. And now why is it we need to understand why is it actually normal, right? So now I need to localize I need to localize these things. So I'm gonna wave my hands here a little bit, and what's going to happen is so let's see. So if we're going to localize at this guy, that we're going to invert this guy, right? So what I am actually looking at is I'm looking at this ring. So I am allowing these elements to be invertible, and times A, right? So, and now what I claim, so this is my stalk, right? This is my localization at x minus 1, where I'm allowing everything to be invertible except for elements in x minus 1. Well, now if you think about it, then in fact, this guy is, what I claim is that it's actually isomorphic to K. What's the isomorphisms, you may ask, and I will answer you, that the isomorphism should be the following. If you think about what are the elements of A and how they look like, right? We have that x times x minus 1 is equal to 0, which is the same thing as x squared minus x is equal to 0, which means that I am essentially identifying x and x squared. So in fact, all the elements of A essentially look like this. They look like A plus bx mod m, right? Like that. For A, B that are inside K. So these are the elements of A. And so what I'm going to do is I'm going to take this element, A plus bx mod m, and I'm just going to evaluate it at x equals 1. Now, why is this true, right? Why this specific isomorphism should work? Well, that's because, once again, so I am allowing x to be invertible now. So before I had x times x minus 1 equals to 0, but now I can divide by x. So I can just do this, which means that my x is equal to 1. So I need to evaluate. So it looks like evaluation at x equals 1 will work. And in fact, it does. So in order to check this thing, just so say let's call this map phi. Right. So all that we need to do is we need to verify that phi of A plus bx times c plus dx. So these are the elements of A, right? That in fact it's the same thing as phi of a plus bx times c plus dx and things like that, right? And I mean, with this identification of x squared and x, this should be pretty clear that it actually works. So just, are we good with that? Can you do it on your own? I actually did it, honestly. Okay. And actually the same thing would happen if you localize it x. So you're allowing everything x minus 1 to be invertible. So basically you're doing this. And in here, the evaluation at 0 will work. So this will be your isomorphism. Okay? And now we see why is it actually normal. So this scheme is normal because I localize and I get a field. But a field is trivially integrally closed, right? So all of the localizations are integrally closed, despite the fact that on top we don't even have an integral domain. So very, very powerful example, okay? Any questions about normality? So this wraps up my discussion about normality. Okay, so now I'm going to move to the next property, and the next property is factoriality. Okay? So definition, let me subdivide it like this. We say that a scheme X is factorial if all of its stalks are unique factorization domains. Okay?
Does UFD imply integrally closed for rings? Yes?
Yes, it does.
Okay.
Yes, it does. And in fact, I'm going to prove.
Punchline.
And in fact, I'm gonna prove it. No, you didn't steal my punchline, but this is actually the main thing that we need to prove it. Yes, and that's actually one of the reasons why we're considering UFDs is because I mean UFDs are the nicest examples of normal things, you know, so of integrally closed things, you know. So and factorial schemes are the nicest examples of normal schemes, right? So that's exactly right. So. So I'm gonna quickly mention one interesting property of UFDs that I'm not gonna prove. I'm just gonna take it for granted. Look it up. No. If A is a UFD, then AX is a UFD. Okay? So I'm just going to state it. I'm not going to prove it. Just ring theory fact. And the proposition that I'm obviously going to prove is the following one. So this proposition. So if A is a UFD, then A is integrally closed. Okay? And the proof of this fact is the following one. You know what? Let me actually reformulate it. I'm going to make it in the form of properties, like that. I'm gonna cheat. This is the first property that I want to mention, and I'm going to mention the second property. And this property was proved by Mr. Pat Naylor last time. And this is the property that if S is a multiplicative subset of a UFD A without 0, then S inverse A is a UFD. Okay? It's the same thing that we had for integrally closed, right? So any non-zero localization ends up to be of a UFD ends up to be a UFD. And so from here we see with this fact we immediately see that any So any if A is a UFD, then spec A is factorial. Right? So if A is a U of D, then spec A is factorial.
Do you know why it's called factorial?
Factorial? Because we factor.
Okay.
Make sense? Yes. Yeah. We can factor nicely in there.
Oh, sure.
Yeah, okay. So now let me prove this fact and what this fact would imply, right? Yes, what's up?
Is the backwards true? The
Is
converse?
the converse? So no, it's not. It's not. Just like for normal schemes, just like right, we can have a normal scheme that is not where the original ring is not even an integral domain. And here you can also have something something that is like the what is it? You can have a scheme that is factorial, but the original ring is not a U of D,
I
right?
think the same example we just did proved that because fields are trivially UFDs.
Well, he has some example with respect to elliptic curves. Maybe I could just mention it. Just give me a second. The converse need not hold. See exercise 5.4n, which we're gonna go through. We went through it before the class, right? In fact, we will see that elliptic curves are factorial, yet no affine open set in the spec of a unique open set is the spec of a unique factorization domain. Okay, so elliptic curves are going to be a good example of these things, but we're going to see them in chapter 19. Long way to go. Okay, so. But anyways, so I'm gonna give, if I'll have time, I'm gonna talk about this example. In fact, the example that we all discussed together. Proposition: if A is a U of D, then A is integrally closed. Here's what we're gonna do, right? So I mean, what do you do, right? You take your polynomial f of x, you take it inside ax, and so it's going to be monad. Alpha is going to be a root of f of x. And we're going to say that alpha is in fact in the fraction field of A. Since alpha is in the fraction field of A, then we know that alpha is of the form A over B, where both A and B are in A. Right? But A is a U of D. So what I'm going to do is that without loss of generality, I will assume that there is no common irreducible that divides both of them. Does that make sense? So this is like GCD is 1. Right? So without loss of generality, assume that no irreducible of A divides both A and B. And now, actually, I'm going to proceed with the proof, and I'm going to proceed exactly in the same way as the rational roots theorem. So let's write down our polynomial. So what do we have? We have a over b to the d. So here I'm writing f of x, essentially evaluated at a over b, plus cd minus 1 over a over b times a over b to the power of d minus 1. And so on, plus C1 A over B plus C0 equals to 0, right? So A over B is a root of this polynomial, multiplied by B to the D. And the way I'm going to do it is this. So it's A to the D, and then I'm going to pull out B outside. So this is just going to be CD minus 1 AD minus 1, plus, and so on, plus C1 so let me think about it. So C1 A B to the D minus 2 plus C0 B to the power of D minus 1. Right? You believe me? And now we notice that B must divide A to the D. Right? But we know that no common irreducible divides A and B. Divides A and B. So let me write this down. Since no common irreducible. No irreducible. There's no. I'm going to say it. Since there's no reducible in common that divides both A and B, B must be a unit. Okay? And if B is a unit, and A, we see that alpha equals A over B must lie in A itself. So, and this is precisely what we need to prove, thus A is integrally closed.
Where did you use the MD?
I used it over here. So I have A over B, right? So I can write it like this. And when I'm writing this statement, so assume that there is no,
Oh,
yeah, right?
yeah.
There's no common irreducible that divides both of them, right? So it's like, so this, what is it? I believe there's this even notion that every U of D is a GCD domain, right? Something like that, right? And what I'm saying basically in here is that GCD is 1.
Yeah.
Yeah, right? So without that, I can't. Okay? Any questions about this? Yes.
So is it more generally true that if A is a UFD, then it's integrally closed?
I think that what should be, like actually this is a good question. Like if A is a GCD domain, right? Every U of D is a GCD domain, but the converse need not hold. I don't know.
Because, yeah, UFDs, it's equivalent to GCDs existing, and then there being this ascending chain condition on principal ideals.
Right.
I don't see where that other condition comes into play here, so probably.
Probably you're right.
GCD.
Yeah. Probably it should be a GCD domain, then it's integrally closed. Yeah, that makes sense. Okay, any other questions about this? So you see, so far it's all just ring theory. So now, what does this thing actually tell us? It tells us that if A is a U of D, then spec A is factorial, and therefore it's also normal. So U of Ds are the nicest examples that give us normal schemes. Now, in terms of what normal schemes are there, like right? There's like that arise from U of Ds. There's tons of them, right? There's Z. There's what is it? There's Gaussian units. There's Kx, where K is a field, and right, and like in anything, any number field with class number 1. So tons of things. Okay, so let me give you some examples now of so examples. And now there's going to be many of them. Let's go for example 1. So let K be a field, right? So K is a field. And the question is the affine n-dimensional scheme factorial and normal? And the answer is yes, it is. Why is that? All right, if you recall what this is, actually, and this is just spec A, where A is just a ring of n-variate polynomials, right, over K. Now, as Nick remarked, we can use this part 1 over here, that if A is a U of that if A is a U of D, then A adjoint X is a U of D, right? So in our case, K is a field, so Kx is a U of D. Kx is a U of D, therefore Kx1, X2 is a U of D, and so on, right? So coming back to our example, that guy is a U of D, even though it's not a PID in general. Like, I mean, in univariate case it is, but more than one variable, it's not. Okay, so once again, so because this is U of D, we immediately conclude that this scheme is factorial and normal. Okay. 2, the projective n-dimensional space. And there, Mr. Patnair remarked that, which once again I skipped so many things. It looks like locally, this is affine, right? And we just proved that everything affine is normal, right? And because, I mean, this is sort of this normality condition is a Stalk local property, we know that this guy is also going to be normal. Okay? Good? Example number 3, probably the most obvious one, if you would consider spec Z. So this scheme is clearly normal, in fact, factorial, right? Why is that? Z is a U of t, right? And everything follows from there. Okay? Now let's see some tricky examples. Okay? So first, I'm going to start with the rather interesting example that I very much enjoy doing. Basically, on the construction of, I don't know, it's like sort of an equivalent of adjoining root of something to whatever. Let's see. So this is example number 4. The problem looks like this. So he formulates it for general rings. I'm going to restrict my attention only to Z. Okay. So let our ring be 2 inverse Z. Okay. So I'm allowing 2 to be invertible in this ring, and I'm considering this new ring, which I'm defining as follows. It's going to be A adjoins Z mod Z square minus F, where F is just some element of A, right? So. Right, and I'm assuming that Z square minus F is irreducible in A adjoins Z. So here's problem A. Problem A was that suppose that F has no repeating prime factors. Has no repeating prime factors. Show that B, so spec B is normal. Right? Or the same thing is B is integrally closed. Right? So that's what I'm going to do. I.e. B is integral. Or maybe I'll form it like this. Show that B is integrally closed. Okay? So essentially I'm looking at the construction of this form. So 2 inverse Z adjoin root F. Right? That's what it is. So let's prove this fact. Well, I mean, what do I need to do, right? I need to take a polynomial, like as usual, I guess I'm using Z, just like in his notes. So f of Z is in B adjoin Z. It's monic. Alpha is the root of f of x, of f of Z, I'm sorry. Alpha is the root of f of Z, and alpha is in the fraction field of B. Okay? And further, what I'm going to do is I'm going to suppose that it's actually in fraction field of B, but it's not in B. Okay? Cool? So now what we notice is, I'm sorry. Z is a wrong thing to do, wrong, right? Because Z is already taken. So I'm going to use T over here. This is bad. So this is f of T. Okay? Capital F, just like in his notes. So now if I recall correctly, what's going to happen next is so I'm looking at this f of T, and I'm saying, okay, just by the way we defined it, right? So this is this root of f. So we can sort of naturally produce this second polynomial f bar of t, which is essentially sort of arises as a result of conjugation, as a result of conjugation of z, right? It's the same thing as, and now what I'm going to do is I'm going to replace my f of t with a new polynomial, which I'm going to call q of t. This q of t. Oh, no. So let me call it, I'm going to just replace f of t with this f of t bar times f of t. And now if you think about it, this guy should be, in fact, in it should be, in fact, in A of t. Now, if you think about what I'm actually doing here, I'm just computing the norm, okay? So it's like, I don't know. So if I, like before I had root 5, right? I'm computing the norm of root 5 by multiplying it by its conjugate, right? And what I'm getting is something on top, right? I'm getting an integer. I'm basically mapping the element in z root 5 in z, right? So this is what is going on. So by doing this kind of replacement, I end up in AT. Now the next thing that I want you to notice is I want you to take a look at alpha and say, okay, how does alpha look like, right? Alpha is an element of B. Maybe I should move to the other direction, the other board. So what is alpha? Okay. So alpha has a very precise form. Let me call it, oh God. Okay, let's call it just A plus B, Z, right? And I'm taking my A and B in where? Well, now they're in A, right? No, they're not. They're in the fraction field of A, right? Now, the next thing to note is that my alpha is in fact of a very is in fact a root. Let me tell you. I just want to make a mistake here. So he uses G and H. So let me stick with his notation. Okay. So G plus H. There's G and H over here. And now the next thing that we note is that that alpha is a root of Q of t, and I'm just sort of artificially constructing a polynomial of which it is a root. So it's t squared minus 2gt plus g squared minus h squared f, and this is a polynomial. This is at the moment it's a polynomial in the fraction field of A adjoint t. Okay. So alpha is the root of this thing, right? And we're assuming that alpha is of degree 2, not of degree 1, okay? So what I'm going to do is I'm going to say, okay, well now this must be sort of a minimal, some kind of a minimal polynomial of this thing. So which means that for this polynomial f of t that we had before, which has coefficients in A of t, is divisible by that guy, okay? So thus, f of t is of the form p of t times q of t, and its coefficients are in A adjoint t. Okay? Well, alpha is a root of that guy, alpha is a root of that guy. So this is a minimal polynomial, so it must divide this thing. And now what is happening is I'm just going to apply the Gauss's lemma. I'm going to say, well, by Gauss's lemma, well, this guy on top has coefficients in A. So alpha is a root of some monic polynomial with coefficients in A, but this guy has coefficients in A. But then it means that this guy must have coefficients in A. So I conclude that QT, Q of t, in fact has its coefficients in A. So 2g and g squared minus h squared f both lie in A. Okay? So this is what is happening. And now if we're going to set g equals to r over 2 and we're going to set h equals to s over t, right, for some elements in A. So r, s, and t are the elements in A. Okay? So for r, s, t in A, then in fact, what we're going to see is we're going to see that, okay, so g squared minus h square f must be of the form r square t square minus 4s square f divided by 4t square. So there I just basically do the substitution, right? I just plug in what g and h is. Right. So now we're going to stare at it. This is an element in A. So somehow we need to conclude that T is invertible. I forgot how did we come to this conclusion? That this denominator over here should be in fact a unit. Should be in fact a unit. So let me think about this is true.
I think it's because, so, you know, 4t squared divides the numerator in A, right? Because that resulted in A.
Okay, this guy, yeah.
Yeah. So your denominator divides your numerator in A, right?
Okay.
And so you conclude that t squared, since 2 is a unit, t squared divides the numerator.
Mm-hmm. Yeah,
And
yeah.
t squared already divides r squared t squared, so it's
So
gonna
t squared must divide 4s square f.
Right.
Uh-huh.
T does not divide s because you can choose it that way.
Yes, absolutely. Yeah. They must be relatively prime because we're dealing with u of d.
Therefore, t squared divides f, but you assume that has no repeating prime factor.
That's right. Fantastic. Okay. Yeah. So did everyone
Big relic.
did everyone capture it? Right. So let's see again what Nick is saying here. He's saying the following. He's saying that 2 is invertible in A, right? So ignore it. It's a unit. We don't care about it. Now t square must divide that guy. This is an element in A, right? So t square must divide this thing. Well, I mean, it obviously divides r square t square. That's out of question. But now it means that t square divides 4s square f. Well, we don't care about 4. 4 is invertible. So therefore, t square divides s square f. Well, now, just by the way which we look at this s over t, and we can do the same trick as we did previously with u of d's. Because A is a u of d, right? So we can just say that s and t are co-prime in there. Okay? So t doesn't divide s, which means that t squared divides f. But wait a minute, we assumed that f has no repeating prime factors. That's it. Thank you. Thank you, Nick Rolick, Grandmaster of Algebraic Geometry. Okay, so this is the explanation. So therefore we see that in fact it is like this. Ring B is integrally closed, and from there we see that the scheme that we obtained, this spec B, is in fact normal. Now, what happens if it does have a repeating prime factor? Well, basically it's I'm just going to wave my hands here a little bit. Okay, so it's the same idea. So essentially what you're doing, right, is you're looking at this ring, say 2 inverse z, and now imagine, right, you're adjoining some root f, but now it has repeating prime factors. Right? It has repeating prime factors. So in fact, what you could do is you could pull out the square free part of it, right? So you can write it as, say, I don't know, a root f prime, where f prime is square free, right? And so now do the same trick as I did before, right? So then if this a is greater than, what is it? If this a is not just powers of 2, right? In this case, then you would basically take its fraction field, right? And what you're gonna obtain is just q adjoin root f prime, right? And now if you're gonna take its ring of integers, it's clearly going to be larger than this, because in particular it will include root f prime, but this guy doesn't include root f prime, something like that. Does that make sense? So this is what is going to happen here. Right. So I didn't get a chance to talk about fortunately for me, I didn't get a chance to talk about one more exercise, and this is exercise 5.4n, where basically we're answering this question of Diana, and the question was could it be that that the scheme is factorial, right? But the ring on top is not a U of D, and the answer is in fact yes, it could be like that. And an example that Vakil gives is the following. Oh, it looks too ugly. I just don't want to. Okay, it's Q x y localized at x squared plus y squared, and then we take degree 0 part of it. So this is an example of something that is not a U of D. However, if we can cover it with affine things that are U of Ds. Does that make sense? So yeah, come talk to me if you want to, or to Nick, or to Diana, or to Pat, because we all four thought about this problem. Yeah, come talk to us if you want to figure out why is this a valid example. Okay, thank you very much for your time. Yeah, and sorry for taking a bit more of your time.
So you say that it's a spec of that ring,
Yes.
the localization, well, every stalk is U of T.
So yes, let me explain. I'm going to explain to you this way. So this is a ring, right? So this is spec A. What's going to happen is that you can actually cover spec A with the following. So with an open set d x squared plus y squared, like that, union d of y squared over x squared plus y squared. And as it turns out, these two guys turn out to be U of Ds. So if you localize, what they're, both of them basically turn out to be isomorphic to Q adjoin T localized at T squared plus 1. This is a U of D. You localize it, it's still a U of D, so it's isomorphic. They are isomorphic to U of D.
That's how you do the exercise. You don't just show directly, you don't just roll up your sleeves and go.
No. Yeah, and yeah, that's what I said. And in order to see that it's not a U of D, basically what you observe is you observe that xy over x squared plus y squared squared is nothing but x squared over x plus y squared times y squared over x squared plus y squared. Like that, right? So this is, so we basically get, so if I call this element, say, I don't know, R, then this R, in fact, has two distinct factorizations into reducible components. Because if any of those would be reducible, right, then they would have to have a degree in the determinant equal to 1, so there should be square roots somehow at present, but you can't have square roots in the denominators in this case. So, yeah.
You basically did the exercise.
No, I mean, I guess the most difficult, the difficult part is basically to show this isomorphism to Q of T localized, QT localized at T squared plus 1. That's the trick. Yeah. Okay. Any other questions, suggestions, complaints?
Sorry, I think I just forgot what we were doing. What was the point behind this example A or example 4? What were we actually trying to come up with? Is it just an example of a ring that's infinitely closed, or what? Like I think I knew what we were doing, and then I forgot.
Fancy example of a normal scheme.
Yeah. Okay,
Yeah, it's,
that's all it is. Okay. It's not like,
yes.
It's not like something, but not
This is
something.
something
It's
you
just
do in
normal.
number theory all the time.
So yes, I guess this is a good yeah. I should have told you. I should have told you this. Yes. This thing is very number theoretical. This has a very number theoretical flavor. Okay, because this is basically what you're doing, right? So I'm sorry for taking. If whoever wants to leave, please leave, right? But I mean, to me personally, once again, I would tell you about my enlightenment that I got from the textbook of Silverman, when he actually mentioned that then what we know as class groups of number fields and things like that, and Picard groups in an algebraic geometry. These are complete analogs. Like Picard groups are analogs of class groups, and this is essentially, you are looking at this very number theoretical ring. Right? This is a very number theoretical thing. That's what algebraic number theorists study. You're looking at it from the perspective of algebraic geometry. That's what you do. Okay? And I'm fairly certain that if you would compute something like of its like class group, right? That's the precise. I mean, you define the Picard group on it, and it will.
The scheme is the class group of the number.
That's right. It will be precisely this thing. Yeah. So it's all about. It's the only reason why I did it is because of this number theoretical construction. And remember this example of z root negative 3, right? Like f equals negative 3. Okay. So somehow very similar in flavor, right?
But it's, yeah, my question was like, because we just showed directly, that it was integrally closed, like we didn't go through the whole UFD route, and there was there's.
No, UFD arises at the very end, right? UFD does arise. It arises at the very end.
Sorry, yeah, you're right. So like B itself.
Yeah, well, then A is a UFD, yeah. B
Yeah.
doesn't have to be.
B, and that's what I'm getting at.
B doesn't have to be A of
So
D,
that's-
but that's why we're doing this conversion, right? That's why I'm multiplying
Yeah.
by the conjugate in order to get to this A.
But the
You know?
example is something that's normal, but you didn't have to go through the UFD route, like it might not be, because UFD, spec of a UFD will be normal.
Will be normal,
But
yes.
It's not necessarily true that, I guess, that a normal scheme has to be spec of a UFD.
UFD for sure.
But that's, so I think I think that's.
Ah, oh,
That's
okay,
probably
okay.
That's like, because it's not
Normal
true in
scheme.
general that B is.
Normal scheme. Okay. So I guess what you're telling me is that this guy is probably not a UFD.
Yeah, no,
That's
if
fine,
the
that's
class
fine.
number's not 1,
That's
If the class, very good point. Yeah. So if the class number of this guy is not 1, then we immediately know that it's not a UFD. But nevertheless,
Okay.
this
No,
is the
okay, that's what I thought was happening.
Yeah.
I just need to know number 3.
yeah.
Okay.
But I don't know. Is B integrally closed?
it will always be integral.
It is integrally closed, but it's not a UFD. Yeah. Okay.
That's-
Yeah.
Okay, so it is.
Yeah, and that's what I showed. I showed that it's integrally closed. That's because that was my the essence of my proof. Fantastic. Okay, yeah.
Cool.
Okay, that's it? All right.